Hi guys, my name is IBM and I welcome you to my YouTube channel. Today I've decided to solve Physics 9702 paper 5. This is planning, analysis and evaluation, and I'm only going to solve two components, 5.1 and 5.2, because 5.3 is the same as 5.1. So without wasting time, I would like to take you to the question paper. So this is the question paper. It's May-June 2022. 970251. The paper is supposed to be 1 hour and 15 minutes. So I'll try my level best to try and save time and finish this on time. But of course, I'll try to explain a lot of things, so I may take a little bit of more time. I may take more than 1 hour and 15 minutes. So the paper is supposed to be 30 marks. This is actually supposed to be the hardest paper in A level because students tend to be unable to plan experiments because they cannot really plan everyday activities. But yet this is supposed to be a very easy paper because you use your own knowledge and understanding to come up with a workable experiment in the laboratory. So let's start. Two parameter plates each of area A. So they are each of area A, and we notice that they are rectangular, so it means the area A will be length times width. So I'll measure L with a ruler and I'll measure the width with a ruler. So if I know that already, I have a mark. By a small distance D. D is a very small distance, so I may most likely use a vernier calipers to measure D. As shown in the figure, the plates are initially charged using a power supply, so I must add a power supply to initially charge these plates. So I need a power supply to charge these plates. So they are initially charged. So I'm going to add a power supply. Maybe let me put it here. I'm just trying to draw the skeleton of how my experiment is going to look like. So I'll need a power supply, a DC power supply. So I'm soldering the power supply to the plates, or I can use crocodile clips. Okay, then the plates are then connected to an uncharged capacitor. So because the plates are going to be connected to an uncharged capacitor, I have to break this. I'll have to break this. So I'm going to introduce a two-way switch. So that the plates can be charged by pressing the switch in one position, and the plates can be discharged by placing the switch in another position. So let's have another position for the switch here. So this can be a wire which goes to the capacitor, so I just need another wire from the other end. So I'll need a capacitor which must be in parallel. This is the symbol for the capacitor. Okay, so the potential difference V across the capacitor is measured. So I'll put a voltmeter across the capacitor. It is suggested that V is related to D by the relationship V W over V equals to 1 plus C D over KA. Okay. So where C is the capacitance of the capacitor, so C is going to be the capacitance of the capacitor, and K and W are constants. So K and W are going to be constants. So K and W are going to be constants, but I should also ensure that the area of overlap of the plates is constant. I should also ensure that the capacitance of the capacitor also remains constant. And of course, if I use the same capacitor, I should always ensure that it completely discharges. So to ensure that the capacitor completely discharges, I'm going to put a switch in parallel with the capacitor, so that when I close this switch, the capacitor is short-circuited and completely discharges. Okay. So I'll call this, I may call this one Q, this P, and of course this is a two-way switch. Okay, so that side of the circuit is complete, but of course I need to remember I have to adjust D. So I'm going to hold the upper plate with maybe strings so that it can easily be adjusted. So I have a clamp somewhere here, a stand somewhere here, where I'm going to attach I will put a wooden rod or a rod. I'm going to clamp a rod, and I'll have, of course, I'll have strings attached to the capacitor plate, to the plates, so that these strings can hold the upper plate. So that I can easily adjust by just I can easily change D by just lifting the upper plate vertically upwards. Okay, then what is missing? I think that is all. So let me go to which graph I'll plot. Because we are investigating V and D, I'm changing D personally. So D is going to be the independent variable. Remember, the independent variable is that quantity that you change as the experimenter. And V is going to be the dependent variable. Of course, the dependent changes when the independent is changed. So I'm going to make whatever is related to the dependent a constant. The subject. So V is the dependent. So I will say 1 over V is the subject, is equal to, I'm dividing by W everywhere. So it is 1 over W plus. Remember, D is the independent. So I should also separate it. So I'll have C divided by K A W times D. If I compare with Y equals to M X plus C, remember I'm investigating V and D, so I'm going to plot a graph of 1 over V against, because we normally prefer to put the independent on the vertical axis or something related to the independent on the vertical axis. So I'll put 1 over V against D. And of course, this is going to be a straight line. Now that is the analysis part. This is going to be a straight line. It has a y-intercept, so not through the origin. Not through the origin, not through 0, 0. And what is the gradient of this line? The gradient, M is going to be C over KAW. So the gradient is C over KAW. So they want us to determine K and W. So gradient is equal to that. So it means K is going to be equal to C divided by A times W times the gradient. And then W is the 1 over W is the y-intercept. Y-intercept is equal to 1 over W. So which means W is going to be 1 over the y-intercept. So for the procedures, I will mention what I'm going to be measuring. The measurements taken, I will measure D using a vernier caliper. I will measure L and W using a meter ruler or a ruler. I will measure V using a voltimeter. And I will need the capacitance. I will need the capacitance. Of course, to measure the capacitance, I will need the time of discharge. So I'll need the time of discharge. If I know the time of discharge, I know V, then I know that V is equal to V naught e power negative T over RC. This is where RC was the time constant, if you remember your knowledge of capacitance. So it means I can find capacitance from this expression here. Then the control variables, I have mentioned that capacitance should be constant, area of overlap should be constant, and I think that is all. The capacitance should be constant, the area of overlap should be constant. Then analysis, I've said we shall plot a graph of 1 over V against D, straight line, gradient is that, K is that. Safety precautions, of course, for safety, I may wear gloves to prevent electric shock when I touch the metal plates, because these are metal plates. They are most likely going to get, they may be carrying electricity. So I may wear rubber gloves in order to prevent electric shocks. I think that will be all. So now I can put this in writing. If I draw the diagram, I'll tell the examiner that in this experiment, whichever way you write your SC, as long as you write all the marking points, it doesn't matter. So in this experiment, I think let me leave the first top. In this experiment, D is independent variable. This is the independent variable, and V is the dependent variable. So this is the dependent variable. And then which quantities will be kept constant? We have mentioned one of them. I will keep the area of overlap of the plates constant. I will keep the area of overlap, that is A, of the plates constant. So I'll keep the area of overlap of the plates constant in this experiment. Okay, then I'll first of all draw the diagram, my diagram here. So let me make this to be the table. You can always draw a better diagram with a pencil. Mine is just a guiding, it's just like a guide. So I'll draw the plates somewhere here. First to draw the upper plate. So that is the upper plate. So I have to try my level best to draw the bottom plate. It's not something very easy, but you can always be creative in your diagram. Okay, so I've tried my level best to draw nice looking plates. You can draw a better diagram. So I'm assuming the plates are on the table. So I'm placing here my stand. And I'm going to clamp a wooden rod or whatever I wish. It could be the clamp. So all I want is to be able to adjust D by simply lifting the upper plate. So for that case, I'm just using strings. So I will attach strings on these plates, on the upper plate, using whatever method I wish. Okay, so I have strings. These are strings which are attached to lift the upper plate, because remember I should be able to adjust the distance. I should be able to adjust the distance D. This distance here is D. I should be able to adjust it. So this is the stand. And these are strings. I want my diagram to remain neat. Okay, so I have strings there used to, of course, whatever way you use to attach them. Maybe you can add here cell tape. You can use cell tape. You can use glue tack or glue, whatever. So these are the metal plates, but before I label, I want to finish the whole diagram. So remember I said I have to add a power supply. So I'm going to add a power supply. Then I need a wire which goes to a two-way switch. So I said I need to put a capacitor. So this is the symbol for a capacitor. And I need to put a voltmeter across the capacitor to measure V. I said I may need to short circuit the capacitor, so I put a switch here so that is fully discharged. So I may put a switch here so that when I close the switch, the capacitor is short circuited so that is fully discharged. Okay, so this is the capacitor of capacitance C. So this is a switch. We have another switch here. Let this be P and let this be Q. Of course, I may also need the PD across the plates before we connect them across, before we turn the switch to position P. So I may put another voltmeter, of course, across the power supply, or I can put it across the plates themselves, but it's the same thing. So I can put a voltmeter here. So this will give me the PD across the plates. So I can now do the labeling. So this is a high voltage DC supply. I have another switch here. It is a two-way switch. Then I have the metal plates. I think I've labeled almost everything. You could also put this on an insulating material. I could put the plates on an insulating material on the bench, but that is fine. Yes, since I have something on top which is made of strings that is going to be used for adjusting the distance D, I may not put an insulating material at the bottom, but still you could make these ones rest. The bottom plate could be placed on an insulator, but if this is a bench or a table, it means most likely it is wooden. Okay, I think I've exhausted everything I need on the diagram, and this diagram could give me at least 3 to 4 marks, I think, because I've given most of the details. 3 to 4 marks. When I put these dots here, it means there is attachment at that point. For circuits, these dots here means that there's a junction there. There's an open wires which are combining at that point. Okay, so now I write my essay, having drawn a very beautiful diagram. Remember to always draw this with a pencil so that in case you want to change to make it look better, you have enough options. It's easier to erase and draw a better diagram. Some of you tend to draw with a pen because you watched the video and the teacher drew in blue. So you should use a pencil for this diagram. Okay. So to collect and analyze data, I'll carry out the following procedures. So I'll carry out the following procedures. What is the spelling of procedure? Okay, I think it is D-U-R-E-S. Okay, the following procedures. Number one, I'll measure the distance D using a vernier caliper. So I'll measure D using vernier calipers. I'll measure D using vernier calipers. Remember, when you measure D, you measure at different points across the plates and obtain the average value of D. So I'll measure D using vernier calipers at different points across plates and obtain an average value of V of D and obtain an average value of D. So when I measure on the left hand side, I can measure on the right, I can measure the other side so that I have an average value of D. So these are two marks in one statement because I said I'm measuring D using a vernier caliper, but I'm also measuring at different points to obtain an average value of D. Remember, for an experiment, the only way to get full marks, you measure. Think of a method of improvement and think of a method of vary, that is MIV. Measure, improve, and vary. You measure, think of how to improve and vary. So I measure using a vernier caliper, and to improve, I measure at different points across the plates, and then I obtain the average. Okay. Then statement number two, I'll now measure, remember I need the area of the plate, so I'll measure the length and the breadth. So I will measure the length and breadth of the metal plates using, because the length and the breadth are relatively big, I will use a ruler, using a rule. And of course, why do I measure that? It's because I want to determine the area and determine the area of overlap from area is equal to length times breadth. Or you can say length times width. So I'll measure the length and the width or the breadth, and then determine the area from length times the breadth. Then number three, I'll now build up the experimental setup as shown in the figure above. So the second statement is, of course, I'm now going to close the switch to position Q. So I'll I'll close the switch, or I'll close the switch to position Q to charge the parallel plates and note the initial PD across the plates. By the way, this PD should be kept constant every time. So, because if it changes, then it will change the PD across the capacitor when the plates discharge across the capacitor. So I will close the switch to position Q to charge the parallel plates and note the PD and note the PD across the metal plates. Which should be kept constant throughout. So the PD across, using this voltmeter here, the PD across the metal plates should be kept constant throughout, because if it doesn't, it affects the values of V, yet we want only to, it affects the values of V across the capacitor, yet we want to only investigate PD across the capacitor and D. Not, so it means we must ensure that the PD across the parallel plates is always the same every time we close the switch to position Q. Okay, then statement. So here I have, I'll close the switch to position Q to charge the parallel plates and note the PD across the metal plates. That one may not give you a mark, but the last part which says which should be kept constant throughout, that would give you a mark. Then statement number 5. Of course, I'm now supposed, after when the plates are charged, I have to transfer the switch to position P. So I will transfer the switch to position P to this position here, so that now the plates discharge across the capacitor, or so that the capacitor gets charged. So I will then transfer. I'll then turn the switch. I'll just use the word turn to position P and record the PDV across the capacitor I record the PDV across the capacitor and the time of discharge. Why didn't I add a resistor here? I have to add a resistor here, for the capacitor is going to be discharged into a resistor. So I'm going to add a resistor here. Sorry about this. because the capacitor must discharge before I repeat the experiment. So I'm going to add a resistor here. That's why I said it's better you draw this with a pencil, because when you're writing the essay, you may realize you need to add something. So I'll add a resistor here. But of course, the voltmeter will be in parallel. Okay. So I'll then turn the switch to position P and record the PDV across the capacitor and the time of discharge through the resistor and the time of discharge through a known resistor R. Okay, so if I know the time of discharge and I know the resistor R, so all I need is to find the capacitance. So step number 6, or before I go to step number 6, I have to repeat. I will have to repeat this step, measurements of V, so that I have an average value of V. So I will have to short circuit the capacitor to ensure that it is fully discharged. So I'm going to short circuit the capacitor so that it is fully discharged, and then repeat measurements of V for the same D and obtain an average value of V. And repeat measurements of V for the same D and obtain an average value of V. So in step 7, I have, of course, to determine the capacitance. So I will determine the capacitance I will determine the capacitance of the capacitor from, of course, you know, V equals to V naught e power minus T over R times C, where T was the time constant. I mean, small t is the time of discharge, R times C is the time constant. Okay, then step number 8. So I will repeat, or I'll add just D and repeat the experiment until I have 6 sets of results. So I will add just D and repeat the experiment until I have 6 sets of results. So now that I have 6 sets of results, the next thing is now to plot a graph, which is now analysis. So step number 9, I'll plot a graph. We said we shall plot a graph of 1 over v against d. So I will plot a graph of 1 over v against d. So in step number 10, of course, it's not actually step number 10. This is just analysis of this. So I'm plotting a graph of 1 over v against 1 over d. Then it is going to be a straight line. A straight line which is not passing through the origin. The straight line not passing through the origin shows that the relationship is valid. So a straight line which does not go through the origin will show that the relationship is valid. Still on analysis, we say that the gradient was equal to C divided by K A W, which implies that K, because they wanted us to find K, so K is going to be equal to C divided by A W times the gradient. Also for analysis, we say that the y-intercept was equal to 1 over W, which also implies that W will be equal to 1 divided by the y-intercept. So what is remaining is just safety. So step 10 is for safety. I will use gloves to prevent electric shocks. So that is when I touch metal plates, or I will avoid touching metal plates to avoid electric shocks. Okay, so I think that if I go through this, I'm very certain that this would give me more than I've written more than 15 marking points. For instance, in this experiment, D is the independent variable and V is the dependent, that is 1 mark. I'll keep a constant, that is 2 marks. Then I'll measure D using a vernier caliper, those are 3. At different points to obtain the average, those are 4 marks. I'll measure the length and the breadth of the metal plates using a rule, that is a mark. And I'll find the area from this, that is another mark. I'll build the experimental setup as shown in the figure above. So in the figure above, I have I have a circuit which has a capacitor in parallel with a voltmeter, and I have, of course, I have strings which are holding this. I have a high voltage supply here. Those are 3 marks. Basically, on the diagram, I have a minimum of 3 marks. If I ignore the rest of the things. So I'll close the switch to position Q to charge the parallel plates, and note the PD across the metal plates, which should be kept constant. So since the PD across the metal plates should be kept constant, that will be a marking point. Then I'll then turn the switch to position P and record the PDV across the capacitor and the time of discharge through a known resistor R. That may not be giving me a mark, but I'll short circuit the capacitor so that it is fully discharged and repeat the measurements of V for same D and obtain an average value of V. So here there are 2 marking points: short circuiting the capacitor so that it is fully discharged and repeating the measurements of V to obtain the value. Those are 2 marking points. How you will determine the capacitance is a marking point. I will adjust D and repeat the experiment until I have 6 sets of results. Then which graph to be plotted, that is a marking point. It is a straight line, that is a marking point. Then the gradient, the y-intercept, then for safety. So it means I've given so many marking points in this experiment. There are more than 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I've given more than 18 marking points in this experiment. The examiner will look for only 15 of these marking points. So I think that gives you some idea about question number 1. Then for question number 2, a student investigates the relationship between the luminosity L of a star and its mass m as for a set of stars known as main sequence stars. Remember, our sun is a main sequence star. It is suggested that L and M are related by this equation here. So whenever you see it's M and L which are being investigated, but one of the variables has a power of n, by all means it will be introducing natural log or log, either ln or log. So S is the luminosity, Z and N are constants. A graph is plotted of log L against log M. So I'm going to make log L the subject of this equation here. So introducing log, I'll have that log of L equals to log of S, Z, M power N. So log of L is equal to N log of capital M plus log of S, Z. So when I compare this with y equals to mx plus c, that is the equation of a straight line. On the y-axis, we have log L. On the x-axis, we have log M. It means the gradient is going to be n. And then the y-intercept, which is c, is going to be log S, Z. Values of M and L are given in the table. So they have given us values of L and M. Calculate and record values of log M power 30, 10 power 30 log L 10 power 28 watts. Include absolute uncertainties in log of M. Okay, so here when I'm finding log and they have labeled it like this, it means I will not press the power of 10 when I'm pressing the log. So let's start with the log of M. Of course, the rule of log is very simple. The number of significant figures becomes the number of decimal places, or you can have more. For example, I have 2 significant figures, so the log of M can be 2 decimal places or more than 2 decimal places, but not less than 2 decimal places. So I'll have a log of 48, log of 4.8. So I have to write 2 decimal places or more. I'll just write 2. So I'll write 0.68 plus or minus. Then log of 6.4 So I'll write 0.81. Remember to round off correctly, 0.81. Then log of 12. So that is 1.08. Remember, it is number of decimal places, not significant figures. Then, so it means when I write this one as 1.1, I've reduced to one decimal place. So it should be two decimal places or more. Then let's say the log of 23, 1.36. Then we have log of 43, 1.63. And then the log of 91, this is 1.96. I said the number of significant figures of the quantity becomes the number of decimal places when I find a log or the ln. The reverse is very true if I find the anti-log or the anti-ln. So if I want to find, let me first also find log of w, I mean log of L, before I come to the uncertainties. So log of 1.4, so this is going to be 0.15. Then log of 3.1, 0.49. Then log of 32, 1.51. We have log of 350, 2.54. We have log of 3600, 3.56. Then we have log of 66,000, 4.82. Okay, so I finished to get the logs. The only thing that is remaining is the uncertainty. So of course, the uncertainty is very simple. You either get the log of the highest minus the log of the exact, or the log of the exact minus the log of the lowest. For instance, for the first one, I'll get log of 4.8 plus 0.4, and I subtract the log of 4.8, as simple as that. So in other words, I'll get log of 5.2 minus log of 4.8. So log of 5.2 minus, I'll just say 0.68. So it is approximately 0.03 or 0.04, depending on what you do. Let me just do it as a full. Let me repeat this. So I'll say log of 5.2. So this is going to be 0.72. 0.72 minus 0.68. 0.72 minus 0.68, which is 0.04. So it is plus or minus 0.04. If you press a calculator for using the full values without rounding off, you may get 0.03. But this is fine. Both values will be acceptable. So this is 0.04. So I'll just do the same here. Log of 6.8 minus 0.81. So this is 0.02. Then I'll get log of 14. minus 1.08. So this is 0.07 when I round off. Then I have log of 25 minus 1.36. So this is 0.04. Then this will be 47. So I have log of 47 minus 1.63. So this is still 0.04. Then I have log of 95 minus 1.96. So this is 0.02. So you notice that I've not pressed the power of 10 because of the labeling of this log. I've not pressed the power of 10. So those are going to be the uncertainties. And when I do this, I'm very certain that I get those 2 marks. So I'll write these values on a paper so that I can plot it very fast and easily. So I'm going to plot a graph of log of L, which is this column here, against log of M, which is this column here. So I'll just write these two columns on a paper. Okay, so draw the straight line of best fit and a worst acceptable straight line on your graph. Label both lines. Determine the gradient of the line of best fit. Include the absolute uncertainty in your answer. So to determine the gradient, to determine the uncertainty, so I'll need the gradient of best fit. I'll also need the gradient of the worst fit, and then the uncertainty. Of course, the uncertainty will be the difference. So let me first go and plot the graph. So this is, I'm going to rotate this page so that I have a bigger space. I think, let me try to rotate this page so that I try to plot it very easily. But still I have to minimize it. Okay. So for the first point, I'm plotting, remember it is log of M against log of L. I mean log of L against log of M. So I start from log of M, which is 0.68. So the scale here is the scale on the x-axis. Remember I say the scale is the value of one small box. So I have 0.8 minus 0.6, which is 0.2 divided by 10. It means one small box is 0.02. So I have 1, 2, 3, 4. That is 0.2 times 4, which is 0.08. So this is 0.68. 68 is to be plotted against 0.15. So 68 against 0.15, I mean 0.15. So the scale on the vertical is 0.5 divided by 10. Each small box is 0.5 over 10, which is 0.05. So I want 0.15. So this is 0.5, 0.5, 0.1. 1.5, those are supposed to be 3. So the point is going to be this one here. It is this point here. Because I'm plotting on a computer, I may not be very precise. So for you, it should be very, very precise. So I think the point is just here. Then the next point is 0.81. So this is 0.82. So 81 is just in the middle of that box, the first box. Then it's against 0.49. So 49. Remember on the vertical each box, why can't I use my calculator to calculate this? So 0.49 divided by the scale on the vertical, which is 0.05. So these are 9 and 9.8, approximately 10 small boxes. So 10 small boxes, approximately 10 small boxes. So 0.49 is very close to 0.5. So it's approximately here. It's almost on the 0.5 box. So I will circle this point. Please, when you are sketching, when you're drawing the plotted point, make sure you use a smaller cross and a circle so that you are not penalized for blobs. Blobs are those big circles. So I want to try and avoid blobs. Okay. Then the next point is 1.08 against 1.51. 1.08, so 1.02, 04, 06, 08. It's against 1.551. So 1.51. Remember, each small box on the vertical is 0.05. So 1.51, those are two boxes. So I think this is going to be the point. I can check with the calculator to be very careful. 1.51 minus 1.5. Then I divide this by the scale, which is 0.05. So that is, what is this? 1.51 minus 1.5 divided by the scale, 0.05. So it's not a full square. So that is going to be wrong. It's less than one small square. So if you make a mistake in plotting, then it means the graph will not be correct. So I have to be very close to 1.5. So this should be a point which is almost 1.5. Okay, because remember one box is 0.05. And then 1.51 is we add 0.01. So it is almost 1.5. So I'll just plot very close to exactly almost 1.5. Then the next one is 1.36. 1.36 against 2.54. So 1.36 on the x-axis, I can calculate this 1.36 minus the closest is 1.2. The scale on the x-axis is 0.02. Those are 8. So on 1.2 I will add 8 squares. So those are 8 squares to reach 1.36. Then on the vertical I have 2.54. On the vertical it is 2.54, so I have to check with my calculator to be specific. 2.54 minus the closest is 2.5. I divide this by the scale, which is 0.05. So on the vertical I have almost half a box. So 2.54, I'll add almost half a box. So 1, 2, 3, 4, 5, 6, 7, 8. Then almost half a box because it's 0.8. So I'll just add almost slightly above half a box. Then I will circle that point. Okay, then the next point is 1.63. So I have 1.62. 3 is in the middle of the box here. 1.63 is against 3.56. 3.56, it's almost one box above, because one box is 0.05. So 3.56 is almost one box on top. So this is 1.63. It is almost here, approximately. Then the next point is 1.96. 1.96, I think it will also be 8 boxes added to 1.8, I think. I can check with the calculator. 1.96 minus 1.8 divided by the scale, which is 0.02 on the x-axis. Those are 8. So I add 8 boxes on 1.8. Then on the y-axis it is 4.82. 4.82 is just after 4.5. Let me just check with the calculator. 4.82 minus 4.5 divided by the scale, which is 0.05. So I will add 6 boxes, approximately 6 boxes on 4.5. So 4.5, I'll add 6 boxes. 1, 2, 3, 4, 5, 6. So I'll go slightly above 6. Go towards 6.4. Slightly above 6. And I'll circle that point. Okay, so these are my points. These are my points. And what remains is to draw the line of best fit. So I have to make sure that all the points fit on the same grid. That's why I have to rotate my graph. Now, the line of best fit, remember, should be a line which is well balanced. The points are well balanced. So that if not all points are on a straight line, then the points above the line should be almost the same number as the points below the line. If you plot it very carefully, most of the points will be on the straight line. So you can try to draw this on a paper and see how best you can do it. Mine is not going to be accurate because I'm drawing on a computer, and I haven't yet got set tools for my computer. So okay, I'll try to draw this again, maybe, but I would have taken this too. This is just for demonstration, so yours should be better. Do not aim at joining the last point to the first point. That is not the rule. The rule is you try to balance the plotted points. So it's what I'm trying to do here. Do not aim at joining the first to the last point, but aim at bringing most of the points on the line and aim at balancing the points above and below the line. Okay, so I'll take this one as my line of best fit. You can draw a better line. The line should not be rotated. When I look at the one I've just drawn, it can still be rotated clockwise. So you can draw a better one. Okay, the next thing, I'm going to draw the error bars very fast. The first error bar was 0.04. Remember, the scale on the vertical is 0.05. On the vertical, the scale is 0.05. But the first error bar is 0.04, so it's slightly less than one small square. So it's approximate. I'll just round off this to almost one small square. Then the second one is 0.02, which is almost half a small square, less than half a small square. This is really very hard. This is really very hard to sketch. It's less than half a square. Okay, the next one is, at least the next one is 0.07, which is this slightly above half a square, one square. So it is going to be almost 1.5. So this one is easy to draw. So almost 1.5. The next one is also less than one small square. I will just round off it to one small square almost. Your error bars should be neat. Mine are not neat because I'm drawing on a computer and this is extremely small, so it becomes very hard for me to draw very neat error bars. But for you should use the scale very carefully. The next one is 0.04, which is also less than one small square slightly. So I'll draw almost less than one small square here and above. Remember to pass your pencil there at least twice so that the error bars look neat. The last one is less than half a small square because it's 0.02. This is also very hard to sketch because it's less than half a small square. Okay, so the line will not look very beautiful, but it's fine. They have nothing. Then the next thing I'm going to do is now to draw the line of worst fit. I don't know how this will look like, but I'm going to try my level best. So for simplicity, I will change the color to red. So there are two ways of drawing the line of best fit. Remember, the line of best worst fit should cross all the error bars. It should cross all the error bars. So you either join the top of the top error bar to the bottom of the bottom error bar as long as all error bars are crossed in the vertical part. If they are not all crossed in the vertical part, then you have to adjust your line of best fit, your line of worst fit, to ensure that you bring all the error bars onto the line. So for example, I'll have this. This is not working. Okay, I think this is working. Okay, so I aimed at joining this point here. It goes through 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 this point here, and I aimed at it touching the bottom of this point, but it failed, so I have to rub it. The bottom of this point is around here, so I should join the bottom because it was 0.02, which is very hard to sketch, so I have to repeat this again. Join the bottom of the top error bar to the bottom of the bottom error bar and ensure that all the error bars are crossed. So I have to check this again. Okay, yes, this one is working. It's kind of working, although it is almost parallel. So I have to label these lines, remember. I have to label them. So when I expand, I think it can be seen when I try to expand this. My lines are not perfectly straight. You can draw a better line, but they're just for demonstration purposes. So this is going to be the line of best fit. This is best fit. And this is worst fit. Then I'll draw the triangles. Let me see if I can draw one triangle for the top. My lines are not perfectly straight, but I have no option other than using them. Okay, so for just for demonstration purposes, I'll use this point here for the blue line. Let me use blue for the blue line. I'll use this point here for the blue line, and I'm going to choose this point here for the red line. Remember, these lines may not be, if you draw on a paper, they are going to be perfectly straight. Mine is not perfectly straight on a computer until I get set instruments on my computer. So I will have these 2 points. For the blue one, I'm using the first point. Then for the red one, I'll use this point. Let me change this to red. Okay, then I also have to look for the bottom end. At the bottom, I also need 2 points for the gradient. So for the blue one, I'll use this for blue. Then for the red one, let me use this for red. Okay. So for the red one, I'm using this. So that will give me the gradient for the worst fit. Then for blue, that is the best fit. Okay, so those are going to be my triangles. Those are going to be my triangles. You can draw better triangles to use them for the gradient. Where you see that it's not possible to use the same triangle, you can always draw two triangles. So for the gradient, I have to write out the points for the best fit. The x value for the best fit, the first y value is going to be this one here. It is 1, 2, 3. So 4.5556 65. So I have 4.65 minus this point here is 1, 2, 3, 4, 5, 6, 7. 7 times 0.7 times 0.05, which is the scale. That is 0.35. So this is minus 0.3. I don't need to add the power of 10 in this case. On the x-axis, I have this point here is 1, 2, 3, 4, 5, 6. So 6 times the scale, 6 times 0.02, and I add this to 1.8. So that's 1.92 minus, for this point here, these are 8. So I'll say 8 small boxes times the scale, which is 0.02 plus 0.6. So I have 0.7576. So those will be the points for the best fit. Then for the worst fit, I'm going to transfer this to the space provided. So for the worst fit, I have the y value is this one, 1, 2, 3. I subtract 3 from the top. 1, 2, 3, which is this one here. So that is 7 times the scale. And I add this to 4. So that's 4.35 minus. On the x-axis, I have this. So sorry, at the bottom, I have this one. These are two boxes, so that is 0.6. Divide by, on the x-axis, I have this value here. Those are two boxes. 1.82, 1.84 minus, I have one box here, so that is 0.82. So I'll write these values down so that I just go to the page where I have to show the working. You are not supposed to show your working here. I'm just writing it here so that I leave this page at once. Okay, so now I can go back to the normal page. I will have to rotate this back to normal. Okay, so for the gradient of best fit, so you get the values from the graph. So I had 4.65 minus 0.35 divide by 1.92 minus 0.76. For the worst fit, I had 4.35 minus 0.6 divide by 1.84 minus 0.82. So I'll check my calculator. 4.65 minus 0.35 divide by 1.92 minus 0.76. So this is 3.707. You are most likely going to get an answer far from this because you are drawing on a paper. And your answer may be more accurate, is going to be more accurate than mine on the computer. The next is 4.35 minus 0.6 divided by 1.84 minus 0.82. So this is 3.676. So there's a difference. So there is an uncertainty. The uncertainty is going to be 3.707 minus 3.676. 3.707 minus 3.676, which is 0.031. So the gradient is going to be the best value, which is 3.707 plus or minus the uncertainty, which is 0.031. Remember, these are just guiding answers. They are not exact answers because I am drawing only on a computer. When you draw on a question paper, you may get more accurate values because you'll draw a very neat graph and a very precise graph. Okay, so the next thing we shall be seeing are the y-intercept. Do not mind about the time, I must take more time. So determine the y-intercept of the line of best fit, include the absolute uncertainty. So for the y-intercept, do not be tempted to take readings from the graph. Just use the equation y equals to mx plus c. So you'll have c for the best fit and c for the worst fit. So c is equal to the y value minus m times x. So I'll say y-intercept for the best fit, which will be, I'll take a pair of values from the from the best fit line. I'll take these values that I have used here. I'll just take those values. So the upper value is the y value, the bottom value was the x value. So y is going to be 4.65 minus the gradient for the best fit, which was 3.707 times the x value, which is 1.92. I think the gradient is correct. 3.707. Okay. So I just press my calculator. So this is going to be 4.65 minus, open brackets, 3.707 times 1.92. So this is going to be negative 2.467. Negative 2.467. Okay. Then I'll get C for the worst fit. So I'll take the worst fit values. I'll take the first values here. A pair of values on the worst fit line. So this was 4.35 minus the gradient for the worst fit was 3.676 times the x value, which is 1.84. I'm just substituting this equation here. C y-intercept is equal to y minus mx. Y value minus the gradient minus the x coordinate. So this is going to be equal to 4.35 minus, open brackets, 3.676 times 1.84. So this is giving me negative 2.414. Of course, an absolute uncertainty of 0 is not acceptable. So if you have more significant figures, you're most likely going to have you're most likely going to have an uncertainty. So the uncertainty is going to be the difference between these two values. So I'll just say 2 minus 2.467 minus 2.414, which is, of course, I've ignored the negative because it will always be plus or minus. So 2.467 minus 2.414. 2.414, which is 0.053. So here I'll write negative 2.467 plus or minus 0.053. Again, I'm saying this answer is not going to be exactly what you get because you have plotted a better graph on the question paper. So you may get a better answer, but this is a guiding answer. We're just interested in a method. Then using your answer to A, C Roman 3 and C Roman 4, determine the values of n and z. So remember, from the first part of this question, we said n was equal to the gradient. You need not to be concerned with the unit. So n was the gradient. So remember, the gradient was best fit gradient was 3.707 plus or minus. The absolute uncertainty was 3.707 plus or minus 0.031. So that is n. Then to find to find z, remember the y-intercept, I think y-intercept was log s z. The y-intercept was equal to the log of s times z. So it means if I get 10 to the power of the y-intercept, I should be able to get s times z. So what is z? Z is going to be equal to, of course, this should be times 10 to the power of what was the log of, on the y-intercept, we had log of L. So this is going to be times 10 to the power of 28. When I get the y-intercept, when I get the anti-logarithm, I multiply by the power of 10. So Z is going to be 10 to the power of the y-intercept. I multiply this by 10 to the power of 28. That is the power of 10 on the vertical, divided by S. So I'm now just going to substitute. So this is 10 to the power of the y-intercept. I'm considering the best fit value. So y-intercept is 10 to the power of negative 2.467. Then times 10 to the power of 28 divided by S, which is 3.85 times 10 to the power of 26. Let me first press the calculator here. 10 to the power so I'll just say shift and log of negative 2.467, then times 1 exponent 28 divided by open bracket 3.85 exponent 26. So Z is 0.0886. 0.0886. So I need to find the uncertainty in Z. Of course, how do I find the uncertainty in Z? The simplest method to find the uncertainty in Z, since S is a constant, it's only the y-intercept which has a constant. So I'll say I'll find Z for the best value. This is Z for the best value. Then I'll find Z for the worst value, which will be 10 to the power of the worst y-intercept, which was negative 2.414. Negative 2.414 times 10 to the power of 28 divided by 3.85 times 10 to the power of 26. So this is going to be shift and logarithm of negative 2.414 times 1 exponent 28 divided by 3.85 exponent 26. So this is 0.1001. Yes, I want the same number of decimal places. So the uncertainty in Z is the difference between these two. So this will be 0.1001 minus 0.0886. So 0.1001 minus 0.0886. So this is 0.012 or 0.0115. So I'll just say plus or minus 0.0115. Okay. So I got Z for the best fit, Z for the worst fit, and I subtracted. Another main sequence star has a mass of 3 times 10 to the power of 20 kilograms, the time the luminosity L. So this normally takes us back to the first equation given, which was L equals to S Z M power N. So you can substitute in this equation directly if you want. S was 3.85 times 10 to the power of 26. Then Z, I think we have our Z as 0.0886. Then M, the mass is 3 times 10 to the power of 30. So since we are going to use N, which was the gradient, so shall we ignore the power of 10? So this would be simply 3.0 to the power of 3.707. So this would be 3.85 exponent 26 times 0.0886 times 3. Where is the power symbol here? So I'll say 3 to the power of 3.707. So this is giving me 2.0 times 10 to the power of, is it 27? 2.0 times 10 to the power of 27. Okay. Let me try to check the one which uses logarithms. So if I am to use logarithms, I have that log of L is equal to N, it was N log of M plus log of S times Z. The power of 10 should be the same if this is to be correct. So log of L is going to be equal to N, which is 3.707 times log of 3. Then plus, this was the y-intercept, remember, so plus the y-intercept. The y-intercept for the best fit was minus 2.467. So minus 2.467. Okay, so let me try to find this. So 3.707 log of 3 plus, so this would be minus 2.467. Okay, so I have to get the ant log. So L is going to be 10 to the power of negative of 0.6983. 0.6983. Okay, Of course, when I get the ant log, I'll multiply this by 10 to the power of course, I have to multiply this by the 10 to the power of L was on the x on the vertical, so this will be 10 to the power of 28. Okay, so I will get shift log negative 0.6983 times 1 exponent 28. So this is 2 times 10 to the power of 28. So it gives us the same answer. 2.0 times 10 to the power of, is it 28? 27. So 2.0 times 10 to the power of 27. Okay. So I have used a lot of time. Many teachers do not do this. Even those who record the videos do not record this. They just go through the mark scheme directed from Cambridge. But I try to show you what exactly is expected from you. So it's not an easy work. You should be appreciative. Until next time, see you in 5.2. Bye-bye.